Our interest is to find the energy of a system of charges. Let's start with a system of point charges, and let's consider the simplest of the systems, a pair of point charges. Well, let's say we have a charge q1 and a charge q2 some distance away, a distance say d between the two. How do you find the energy of this system? Well, you should imagine a zero energy state for this system, and then I'll find the work done to configure the system this way. So you could imagine q1 is at rest and q2 is very far away. There's no other charge anywhere in the neighborhood. So q2 is very far away, and it's been brought to the field of q1 by moving it from infinity to this place, which is d away from q1. q1 is at rest. So the work done in that process would be W would be, you have moved q2 from infinity, so potential is 0 there, and to q1 by 4.0d. This is the potential due to q1 at the place where q2 is finally placed. And this is the potential due to q1 very far away where q2 was initially imagined by us. So this is the energy of the system. This is q1 q2 by 4 pi epsilon 0 d. Now you could as well have moved q1 into the field of q2. It doesn't matter. So the energy is this for the system. Now you could also imagine doing this like say q2 was brought to a position which is 2d away from q1 first, and then q1 was moved the remaining d. It doesn't make a difference how you configure the system. The final state matters, and that's why potential energy holds so much of importance for us. It depends only on the state, not how you got into that state from some initial state. So this is the energy of a pair of point charges. You must have a little clarity about what a point charge is. Point charge is an idealization, approximation we do to avoid dealing with the distribution of charge. Every charged body, this is a charged body. It has some dimensions, but its size is so small that we can ignore the size of the charge compared to this distance. That's a point charge. And you cannot think of, well, say, parts of a point charge. Point charge is one unit, and this is what we have. Another nice question here is the system energy. Who has it? Does q1 have it? Does q2 have it? Does the system have it? I think you would say the system has the energy, because we may have done work on q2 and brought it here from very far away position, but if we hold now q2 at rest and release q1, this will fly away. So the potential energy of the system will be converted into kinetic energy of q1. So you've done work on q2, right? You brought it from infinity to this place. This is some object you have brought, pushing it against the repulsion of q1. Though we are not doing calculations of energy and work in terms of forces, this is another nice way of doing it, well, in terms of potential. So the point is, you cannot assume the energy is possessed by the q1 or q2, because you pushed q2 all the way from infinity to this place and you hold it at rest and q1 flies away. How did the energy get transferred if it is somehow possessed by q2? So it is system energy. Where is it stored? Well, you have an interesting answer. It is stored in the space where the field due to charges q1 and q2 is present. So energy can be imagined to be stored in the place where q1, q2 create field, and that seems a very logical thing to do, because it's not quite all right to assume q1 has energy or q2 has energy, because then transfer would be a problem. q1 and q2 interact through their fields, so creates field in the space. So as they change positions, the space field in the space changes, and the energy stored in space is converted into some other form. A bit of an abstract idea, but do remember energy is a calculation. Now, what do you mean by that? When you say, well, say you have a block on a smooth surface and you push it and it accelerates and gains kinetic energy, you say your biochemical energy is converted to kinetic energy. Did you somehow transfer something inside you to that body? No. Well, that's the calculation you have done, and you found this is the, well, it's very convenient to say that. Say, there is a limitation of perhaps the language that you say, well, energy is transferred. Well, something has decreased somewhere, something has increased somewhere, so it's convenient to imagine there is a transfer. So energy is a calculation, and if different ways of calculation give you the same result, you're okay with it, right? Now, once we say energy is stored in space, how do you calculate that? We have a nice system for that. Like we have a so you are saying it's seems when it's, so you are saying it seems logical to imagine energy stored in this space around the charges in the field they create. How do you find the energy stored in this field? A very convenient field, a uniform field between the plates of a parallel plate capacitor. Say this has got a charge of density plus sigma, this is minus sigma, they are d apart, and the area of each plate is A. Now, if you're asked what is the field in the gap, the positive charge creates a field away from it, that's downward, and negative charge towards itself, and each of those fields will be sigma by 2 epsilon 0. The net field here is sigma by epsilon 0 in this space. So, E in this space, this E is sigma by epsilon 0. This sum of fields due to the positive plate and negative plate. Positive plate is sigma by 2 epsilon 0 towards the negative plate, and negative plate is sigma by 2 epsilon 0 towards negative plate, so they add up and give you this field. So this uniform field, we neglect what happens at the edge as well. The field is not exactly uniform here, and there is negligible field outside the plate, so we'll ignore that and say there is only field of sigma by epsilon 0 in the space between the plates, which is of volume. This is A and this is D, so volume AD. Now imagine pulling this plate away by a small amount, say, well, say L. We'll move it by L. You're moving it against the attraction due to the other plate. And what is the attraction due to the other plate? If you consider an element of this charge, dq, the force on that element due to the other field of the other charge is this. That is towards the negative charge. This is the force on a dq element of the positive plate due to the charge on the other plate. Now dq is also in the field of the rest of the charges, but that doesn't matter to us. The field due to all the rest of the charges, the forces are going to cancel out. Those are internal forces. So the force on dq element, if you add up the force on all dq's of the plates, they add up to 0. So when you're looking at the entire plate and planning to move it by, say, L, so this is the force here to overcome. So this is sigma into, and since field is same everywhere for all dq elements, this will be simply q into sigma by this df, and so f would be q by sigma by 2 epsilon 0. And q is sigma a, isn't it? So this sigma squared a by 2 epsilon 0. This is the force. So this is the force of attraction due to the negative charge, and you have to overcome that and move it through L, say. So that force, the work done by the external agent for that would be sigma squared a by 2 epsilon 0 into L. That's the work done. Now if you move it through this distance L, in the extra space that you have created, the field is now again the same value. This distance doesn't matter, right? As long as it's small, the distance is, the field is again same as what you had here. That is the space of AL, extra volume AL, the field is sigma by epsilon 0. So this work done by the agent has created field in this space, and if you say energy is stored in the field, it must be stored in a volume of AL. So this is what you call energy density. That's it. Interesting, right? So this is sigma squared by 2 epsilon 0. That's the energy. This is the energy density of electric field. If the field is of strength E, the energy density is this. So then we can replace this a bit and then say sigma by epsilon 0 is field, right? So this is sigma squared. Sigma squared can be replaced by, well, multiply this with another epsilon 0 square. Sigma squared by epsilon 0 squared will be E squared. So this will be epsilon 0. We have multiplied this, epsilon 0 squared. This is E. So epsilon 0 E squared by 2. Interesting. This is the energy density in electric field. So energy of a system of charges, well, consider just a simple system here. 2-point charges must be imagined to be stored in the field created by them, and energy density in that field is this. We found the energy of a pair of point charges. It came to Q1, Q2 by epsilon 0 D, and we said it should be assumed to be stored in the space where the charges create field. Now let's think of more than 2 charges, say 3-point charges of Q each, the corners of an equilateral triangle, or let's call them Q1, Q2, Q3. It's an equilateral triangle, and the side of the triangle is, say, L. What is the energy of this system? There are multiple ways of doing this. One would be to think of the work done in configuring the system. So imagine Q1 is here and Q2, Q3 are very, very far away. You could bring Q2 into the field of Q1, right? So and that energy would be Q1, Q2 by 4 pi epsilon. This is the work done in bringing Q2 into the field of Q1. Now you bring Q3 into the field of Q1 and Q2. So if you do that, let that work done, let's do the calculation here, that work done in bringing 3 into the field of 2 and 1. Now that work done, well, is going to come out to Q3 was at infinity, so final potential is due to Q1 and Q2. Q1 by epsilon 0 L plus Q2 by epsilon 0 L, that is Q1 plus Q2 by 4 pi epsilon 0 L. What is this? This is the potential at which Q3 is finally located due to the other 2 charges. This is, and initially Q3 was infinitely far away, so this is it. So this is the work done in bringing Q3 into the field of Q1 and Q2. So this is the work done. So the total energy of the system, we have configured the system. Initially only Q1 was present. If Q1 is alone present with no interaction with anybody, it just stays where it is. Whereas if Q1, Q2, Q3 are present like this, if you let them, they will fly away. So anyway, the energy of this system is, well, add this, and I think you can see this is going to come to Q2, Q3 by epsilon 0 D, L, and Q1, Q3 by epsilon 0 L. So this is Q2, Q3 by 4 pi epsilon 0 L, sorry, this L, plus Q3, Q1 by 4 pi epsilon 0 L. This is the energy work done, and this is the energy of the system. Work done is equal to change in potential energy. Initial potential energy was 0 for the system. So this is it. Now this, having done this, maybe next time we wouldn't do this. You can see that you can see the energy of the system as energy of the pairs. So Q1, Q2 one pair, Q2, Q3 another pair, Q3, Q1 another pair. Don't repeat the pairs. So, well, when you are doing this calculation, you are basically working out the calculating the work done in bringing the system into this state. So how do you get the result? You don't have to do always this. Well, count the pairs. First pair, Q1, Q2 by 4 pi 0 L. Second, Q3, Q2, Q3 by 0 L. Third, Q3, Q1 by 0 L. and don't repeat the calculation. That is, you don't have to go to again this way 1 3 3 2 2 1. No, 1 2 2 3 3 1. Don't repeat the pairs. So this is the energy of the system of 3-point charges. Well, if they were all equal, it would have been a very simple 3q squared by 4 pi epsilon 0 L. Going back to the calculation of 3 charges at the corners of an equilateral triangle, we counted the pairs and then found the energy, 3 pairs, and we found the energy of each pair. Another way could be, say, this is a generalized formula, sigma qi vi by 2. Now, you might say this seems strange, this 2 here, but let's elaborate that. If you had just a pair, forget this for a moment, if just had a pair, if I do qi vi for this, that is q1 is in the field of q2, I find the potential here, which will be q2 by epsilon 0 L. So q1 into q2 by epsilon 0 L, that will be the energy. If I go to q2 again, do the same calculation, you would have q2 is in the field of q1, so q1 by epsilon 0 L into q2, the same value, and if you add them, you will get well 2q1 q2 by epsilon 0 L. So you must halve it. Why halve it? Why halve it? Either you can treat q1 to be in the field of q2 or q2 to be in the field of q1. You didn't bring both into field of each other, right? q1 was held at rest, q2 was brought into the field of q1. So that's how you calculate it. So when you find the energy this way, q1 is in the field of q2 and q3. Let's calculate that energy. What will that be? q1 into q2 by 4 pi epsilon 0 L plus q3 by epsilon 0 L. This is q1 in the field of q2. If you do the calculation for q2, you will have q2 and then q3 and q1 here. And if you do a similar calculation for, well, q1 again, q3, you will get q3, and this will be q1 and q2. So you see the calculation repeat 2 times. Let me show that here. Well, you have q1 in the field of q2. That is, this first term is the potential at the place where 1 is due to 2. The second term is potential at the place where 1 is due to 3. And then similar calculation for q2. q2, potential at the place where 2 is due to 1 plus potential at the place where 2 is due to 3 plus, I'm trespassing, it should be alright, q3 and potential at the place where 3 is due to 1 plus potential at the place where 3 is due to 2. This should be the energy of the system. Now q1 v12 will be same as q2 v21. Like what? q1, what is v12? Potential at the place where 1 is due to 2, that will be q2 by epsilon 0 L. This is q2 by epsilon 0 L, so this will be q1 q2 by epsilon 0 L. This is q2, and what is potential at the place where 2 is due to 1? q1 by epsilon 0 L. This is q1 by epsilon 0 L, so this will be the same. So q2 v21 will be same as q1 v12. So if you do this calculation, you will get twice, well, what we calculated from work done calculations earlier. So this should be halved. So this should be this q1, and let's call this v1, potential at the place where 1 is due to the other 2. So if I do this q2, you must halve this, right? If you don't halve it, you don't get the right value. So q2 v2 plus q3 v3 by 2. That's what we are writing here, sigma qi vi by 2. Well, so this is the energy of a system of point charges. You can either talk in terms of work done, which you did earlier, or you can look at the system as it is, q1 in the field of q2, q3, calculate the energy, and then leave out q1 from further calculations. That's, instead of halving, you can leave out q1 from further calculation. Then q2 is in the field of q3, do that calculation till you are left with 1 point charge. So what are our options of calculating the energy of a system of point charges? This is one. The other is configuring the system. Let me elaborate. So if there are 3 charges, say Q1, Q2, Q3, you can find the work done in configuring the system. So we have all the charges very far away. Q1 is here, the rest are very far away. Q2 is brought to the field of Q1, then Q3 is brought to the field of Q1 and Q2. That's one calculation. We did that earlier. And then the other is to count the pairs. This is one pair, this is another pair, this is another pair with no duplication. We learned that too. Yet other is this, find the energy of Q1 in the field of the other two, do that with Q2, do that with Q3, and then halve it. Sometimes that's also convenient. So these are the options for you. Now let's do a small calculation with let's say illustrating this point. 4 point charges of Q each are at the corners of a square. They're all Q each. The side of the square is say A. What is the energy of this system? Let's count the pairs. 1, 2, 2, 3, 3, 4, 4, 1. They're all identical pairs. They're all Q's and distance is A. So 4 Q squared by 4 pi epsilon 0 A. Energy of a pair of charges, point charges, Q1, Q2 by 0 D. Q1, Q2 is Q squared and D is A. But that's not all. There is now this pairing. 1, 3, 1, 3. This will be root 2A, right? And this is root 2A. So the energy of this pairs is, there are again two identical pairs there. Q squared by 4 pi epsilon 0 root 2A. This is the energy of the system. Pretty convenient counting the pairs without duplication. The other option would be to find the configure the system. That will be really, well, you will not be using the exploiting the symmetry in this situation. We would have to imagine 2, 3, 4 very far away, bring 2 into the field of 1, then 3 into the field of 1 and 2, 4 into the field of 1, 2, 3. That will be a lot of calculation and you would not be exploiting the symmetry here. The other is, of course, find the energy of Q in the field of the other 3. So that is Q in the field of the other 3. Other 3, what is the potential due to 2? Q by 4 pi epsilon 0 A. And due to 4 also it is same, so twice. Plus due to 3 it will be Q by 4 pi epsilon 0 root 2A. What is that you have done? QI VI for 1. It is same calculation for the other 3 because, well, subscripts really don't matter here, all identical here. And if you do this calculation, you must do divide by 2. This sigma QI VI by 2. This is the energy of the system. So you got the same as earlier, right? So whichever way you do, it's your choice. And well, there are 4 pairs. Sorry, 4 of them. 4 of them. 4 into this divided by 2, so that this will be 2, and you get the same result as up there. This is counting the pairs without duplication. This is sigma QI VI by 2. Sigma, this is sigma QI VI by 2 because this is symmetry here. It's also convenient to do it this way. And we don't want to do that configuring the system. That was just to get an understanding that when you do the sigma QI VI, you are getting double the value. Because when you're doing this calculation sigma QI VI, you're treating 1 in the field of the other 3. And then you're also treating 1 to be creating the field when you're doing calculations for 2, 3 and 4. So either you should treat the charges creating the field or being present in the field. Go back a step. Well, 2 was the field of 1, right, when it was brought into from infinity to this place, right? And then you can do the calculation the other way, like say when you find well, potential at the place where 2 is due to 1, it's like finding the work done in bringing Q1 from infinity to this place. So do one way. So there's the reason why we did that calculation. So anyway, no duplication, count the pairs without duplication. Or if we do sigma QIVA for every charge, halve it. There are 4 charges potentially at the place where 1 is due to other 3 we found out. There are 4 such charges, and then this correlation you have to halve it, right? So in this understanding of energy of a system of point charges, you must either treat the charge to be creating the field or present in the field, not both. What do you mean by that? Well, if you start off with just 1, 2 was brought to the field of 1. And then 3 was brought to the field of 1 and 2. 4 was brought to the field of 1, 2, 3. You don't go back to 1 and again say 1 was brought to the field of 2, 3, 4. It was already there. So either treat the charge as creating the field or present in the field. But if you do both, then halve it. That's what you've done. You've treated the Q to be present in the field of the other 3. You've done the correlation for all the 4 because there is symmetry. Then halve it.